Hello, thank you. I'm Ian Wheeldon, and this is Ben Hatton. We're at the Wyss Institute with Don Ingberg, and also we've worked with Chuck. He's really, I guess, influenced us a lot in this work. So today I'm going to talk about molecules, or from molecules to buildings, some biologically inspired engineering for adaptive architecture. So really the goal of this work is to design new materials from the bottom up that have adaptive and responsive properties, and then to use these for architectural things. And that's why we're here, to have this interaction with the architectural people so we can have a good dynamic with that to organize these materials. And we've seen a lot of this in the last couple of days, and these are a couple of examples of Chuck's work and what we consider kind of top-down adaptive architecture. And that is using louvers to change a facade, and those louvers are controlled by motors and different mechanisms. This is also true in his adaptive fritting, where we've got glass that slides back and forth, and these require mechanical action to have the adaptive behavior. But as Don alluded to earlier, nature doesn't build this way, and in fact it builds from the bottom up. So we have, you know, a structure of, say, the tendon, which is prescribed at the amino acid level. So of amino acids self-assembling, coming together in different fibers, and those fibers into bundles, and that forms the tendon. So nature builds in this way. It builds its complex, interesting materials from the bottom up. And another example of this is microlenses. So this is microlenses from a brittle star. And these are lenses that are formed from silica that focus light onto nerve bundles. So these lenses, though, are a microarray on a bigger sheet. And this sheet, or this plate, is then populated across the arms of the brittle star. And so we have this hierarchical structure, these complex materials that are built from the bottom up. So neither of these two examples, though, are adaptive, and what we'd like to talk about today is some of our work towards making adaptive materials from the bottom up. And I'll show some examples of transformable structures and autonomous self-healing in different composite materials, and then Ben will talk a little bit about our work towards intelligent surfaces and thermal management. So the first being transformable structures and materials, and I think this fits really well with the last talk where he was showing a flower opening. And this is work done by Al Mahadavan at the Wyss, a core faculty there, where he's described or replicated and produced mimetics of pine cones opening and closing. And so when they're wet, they're closed in this really tight structure, and when they dry, they open up. So they've replicated this by a simple system that's just a bilaminate layer of a plastic, of a flexible plastic with a paper backing. And so when it gets wet, when it's humid, the paper swells and causes I guess the structure, the planar structure, to open up, and when it dries out again, it closes up. So we've replicated this idea of transformable structures that respond to the environment. In this case, it's humidity. And so this idea of kind of pushing and pulling water around is actually used quite a bit in different functional materials, or different materials that change shape or transform. And this is another example from the Eisenberg group, where we have a polymer, a hydrogel structure, and inside or embedded in there are different mechanical units, so different pillars, different microscale pillars. And by changing the swelling in this gel, by pushing and pulling water inside the gel, you can actuate the microscale structures, transform the physical nature of the material by pushing and pulling water in and out of the gel. This is also another example, which I quite like, is an array of microlenses that by swelling and deswelling these gels, which form an array of lenses, they can control the optical properties of this material. So it responds to an analyte, it swells, changes structure, and it changes optical properties. So this is another really interesting example that is similar to the hydrogels with microscale structures. And this is a sea cucumber that in its natural state it swims around, is very soft. And then to protect itself, it gets very, very hard. And to do this, it has a very soft material that's I guess on the inside are microfibers or stiff microfibers, and when the interactions are turned on between those fibers, it gets very stiff. When the interactions are turned off, these little stiff bundles are actually collagen fibers, and so when there's a chemical it's a chemical action. So when there's a chemical present, it turns the interactions on between the fibers, and when that chemical is removed, it turns off those interactions. It becomes very soft. So here we have this kind of bottom-up idea that we have stiff collagen fibers. When their interactions between those fibers are turned on, it gets a very hard material, and then it turns off, it becomes soft. So this brings us to autonomous self-healing. This is the second of the things I'll talk about, and then Ben will talk about some adaptive color and surfaces. Autonomous self-healing, though, is, I guess this story kind of starts with not self-healing, but very strong and ultra-tough materials. And there's been quite a bit of work done on nacre, or that's mollusk shells, that are corrosion resistant and abrasion resistant and are very tough. And this property becomes, or is as a result of the structure of these calcium carbonate layers, and this structure kind of provides it with an ultra toughness. So what's interesting about this is people have started to mimic this by creating these layered structures of clay and attaching those together with different polymer structures, and they can replicate this ultra toughness just by replicating the structure of it. But really what's interesting about biology then, though, is that it self-heals. So you can have a bone that it fractures and then it repairs itself, and cells remodel the environment. And this is only really possible because there's vasculature and there's access to the material. And so this idea has been replicated or engineered into different composites. So people have taken this idea that capillary networks are going to infiltrate your material and provide some self-healing, so that they've micro-engineered different channels within the composite, so that when a fracture occurs, a pre-polymer solution and a catalyst come into contact and reseal that fracture. As opposed to just a micro capillary network, an easier way to do this is by creating an emulsion. And so your composite material is within your composite material is embedded these vesicles with a pre-polymer solution, and there's catalysts throughout the material. So when a crack occurs, it opens up a pre-polymer solution that then feeds into the catalyst and closes up the fracture. Just a little bit on intelligent surfaces before Ben describes some of our work. This is really based on the lotus leaf, which is a super hydrophobic surface. Its patterning is repellent to water, and then when water rolls across it, it kind of self-cleans. Also, this is a very interesting video, if you have time to look at it on YouTube. It's by Roger Hanlon. This is an example of an octopus that's camouflaging itself on a rock, and within 2 seconds, as the swimmer comes very close to it, it rapidly changes color. And so this is an adaptive color thing that we're trying to mimic as well. Thermal management is the last idea. And that really gets back to this idea of vasculature, where we're contacting our materials throughout with a vasculature. And I think this is where I'll end, and I'll let Ben pick up with some of our works towards this.
Great, thanks.